Welcome back to Math 103. This is video number 21 on apportionment. Last time we concluded by asking about the apportionment of 42 seats to these 6 states with these populations. We started out looking at standard quotas and asking, does using the standard divisor and using these standard quotas lead under Huntington-Hill to an apportionment of the correct number 42 seats? It turns out that the answer is no, but let's be sure that we understand why. So the standard quotas are given here, and the geometric means, the Huntington-Hill rounding cutoffs, are given here. I've highlighted the one example where ordinary rounding would have said one thing, but Huntington-Hill rounding says something else. So in the case of Vermont, with its standard quota of 2.47 something, that is actually greater than the Huntington-Hill rounding cutoff for a quota of the form 2 point something. So in any example of Huntington-Hill, a standard quota of 2 point something will give rise to this rounding cutoff. And because the quota exceeds the rounding cutoff, we round up rather than down. At the end of the day, the total number of seats given out thus far is 41. That's short of the total required. So we're going to need a modified divisor. And since we have too few seats, that is, too few cookies, we're going to need a smaller cookie cutter to produce more cookies. What's a good candidate for a modified divisor? First, we need to know the standard divisor, which turns out to be 404,000 and something. So 17 million people total, spread out among 42 seats, means a standard congressional district would have 404,762 people in it. So we need something a little bit less. Let's try 404,000 and see if it works. In fact, it does. It's good practice to go through this computation and make sure that you understand it and that you're getting the same numbers. Here, Massachusetts has a population of 7 million. When we divide that by the modified divisor of 404,000, we get this modified quota, 17.32 something. Right? Since it is 17 point something, the rounding cutoff will be the square root of 17 times 18, so the lower and upper quotas of this number. And that turns out to be 17.49. This is clearly lower than that, so we round down to 17. Great, so Connecticut, 9.4 something is the modified quota, so the rounding cutoff will be the square root of 9 times 10, the integers on either side of this quota, and since the quota is less than the rounding cutoff, we round down. We go through and do the same for all the states, and it turns out that here there are actually 2 examples of states where their modified quota would have been rounded down by Webster, but is actually rounded up by Huntington-Hill. And the example of Rhode Island is particularly striking. What this illustrates is that you really need to carry several decimal places of accuracy, at least 3 decimal places worth of information, to be sure that you're really able to compare accurately the modified quota and this geometric mean. So once we have enough digits, we can be sure that this modified quota really is greater than the rounding cutoff, so it gets rounded up. Vermont also has a quota that's greater than its rounding cutoff, so it too gets rounded up by Huntington-Hill. And sure enough, at the end of the day, thanks to the way the Huntington-Hill rounding works, the total number of seats apportioned really does equal 42. Great, that means that these numbers in this column do tell us the Huntington-Hill apportionment. How many seats does Connecticut get according to Huntington and Hill? 9. How many seats does Rhode Island get? 4. Okay, so this is the apportionment according to Huntington and Hill. Not surprisingly, the Huntington-Hill method has its pros and cons. Since this is the apportionment method that's actually used currently for the U.S. House of Representatives, let's end on a positive note and break with our tradition in this course. Let's discuss the cons first and end with the pros. So the Huntington-Hill method can produce quota violations. Okay, so this is a little bit unfortunate. In fact, it turns out any divisor method, any modified divisor method, is going to be vulnerable to this flaw of producing quota rule violations. Another flaw is that the Huntington-Hill method has a bias in favor of small states. Remember, Jefferson had a bias in favor of large states. Huntington and Hill have a bias in favor of small states. To see how that would be, this can be understood by comparing the square root of 2 times 3, okay, that's 2.4495 approximately, which differs from 2.5 by a fair amount. By contrast, the square root of 100 times 101 is 100.4988, which differs from 100.5 by only 0.0012. So what's the significance of these numbers? Right? So what I'm exploring here is how far apart the Huntington-Hill rounding cutoff is from the Webster rounding cutoff. For a small state whose quota is 2 point something, so that this is the rounding cutoff that Huntington and Hill want to look at, for a small state like this, the difference between the Huntington-Hill rounding cutoff and the Webster rounding cutoff is fairly substantial. But for a larger state with quota 100 point something, there is only a very small difference between the Huntington-Hill and Webster rounding cutoffs. So how does that affect things? A small state, such as Vermont in our example, has, in some sense, more room in which its quota could land in round-up territory, and less room in which it could land in round-down territory. So if its quota lands anywhere from this number up to 3, it gets rounded up to 3, and if it's between 2 and this number, then it gets rounded down to 2. So there is more space between this number and 3 than there is between that number and 3. So Huntington and Hill, in some sense, give a small state like Vermont a little more opportunity to get rounded up. Okay. The difference between these cutoffs becomes insignificant when we look at larger states. And now the pros. First, the Huntington-Hill method avoids the Alabama paradox. It also avoids certain other paradoxes that we don't discuss in this course. There is another important advantage that Huntington-Hill has that led to its adoption in 1941 to apportion the U.S. House of Representatives, and is a reason that keeps getting brought forward for maintaining the Huntington-Hill method instead of switching to a different method. Okay, so here's the thought process. Differences in population per seat from one state to another can't be avoided entirely. So we've seen in examples that sometimes you get one congressional district that's a little more crowded and another that's a little bit less crowded. That can't be avoided. That can't be avoided entirely. But each apportionment method does hope to minimize those disparities. The advantage of Huntington-Hill is that it minimizes the relative differences in population per seat. No other method does a better job of minimizing the relative differences in population per seat. So let me explain what relative differences means. Look back at our example of apportioning 38 seats among these states with these populations, according to Huntington and Hill. Here, Maine and Vermont have very high population per seat. In other words, they have crowded congressional districts, whereas Connecticut has a fairly low population per seat, so that its congressional districts are comparatively uncrowded. Now, how large is this disparity? How can we measure it? Well, we can measure it in relative terms as follows. 500,000 divided by 422,000, etc., is approximately 1.1842. So how much greater, how many times greater is the population of a congressional district in Maine than in Connecticut? 1.1842 times greater. So Maine has about 18.42% more people per seat than Connecticut. Now, if the relationship between this number and that percentage mystifies you at all, don't worry, we will come back to this in detail in a later chapter. The point is that if you are willing to believe that Maine has 18-point-something% more people per seat than Connecticut, notice that this is the largest disparity between states. Maine is the most crowded and Connecticut the least crowded in population per seat, i.e. population per congressional district. What's good about Huntington-Hill in this context? The Huntington-Hill method always finds the apportionment which minimizes the disparities between states when we're measuring those disparities as relative differences, proportional differences, percent differences in population per seat. Right? So in a certain sense, the Huntington-Hill method is, quote-unquote, the best method according to a certain way of thinking about what best means. We've now studied 4 different apportionment methods, each of which has actually been used in American history to apportion the U.S. House of Representatives. We've seen also that there are some arguments that Huntington-Hill is better than its competitors. But we've only looked at 4 methods so far, and we can still ask, what apportionment method out there does a perfect job of doing the things that an apportionment method should do? Well, here's the bad news. Just as Arrow's theorem tells us that there is no perfect voting method, there is another theorem, the Balinski-Young theorem, which says that there is no perfect apportionment method in the following sense. And notice that this theorem is relatively recent. It was proved only in 1982. So they concluded that every apportionment method has at least one of the following flaws. It violates the quota rule some of the time, or it produces paradoxes, such as the Alabama paradox or certain others, in some apportionments. So in other words, it is impossible for an apportionment method never to mess up in this respect, and also to never mess up in this other respect. So among our 4 methods that we've discussed, Hamilton's method has the advantage that it never violates the quota rule, but it has the flaw that it does give rise to the Alabama paradox, and it turns out certain other paradoxes that we don't discuss in this course. How about the modified divisor methods, the other 3 methods we've discussed? Well, they all are vulnerable to violating the quota rule, but they have the advantage that they're not vulnerable to creating the Alabama paradox, nor are they vulnerable to certain other paradoxes that we don't discuss in this course. Great. So, where does that leave us? We are still left asking which is the best apportionment method, and that is still controversial. So yes, there are certain arguments in favor of Huntington and Hill, but there are arguments that people are still making in favor of other apportionment methods, especially Webster. So the question of which apportionment method to use for apportioning congressional seats among states may well be a hot topic of debate again in your lifetime. This is why this topic is part of a liberal arts mathematics course. This is part of your general education. This is something that you, as an educated person, need to be aware of and able to think about.